Well, good evening and welcome to Copernic's Friday Night Livestream, or FNL as I'm going to start calling it, program. Um, we're sad, unfortunately, that we can't have you have you here in person, but we're actually very glad that there's technology available to bring us together so that we can, in fact, learn from each other. Right now, I'm doing this live stream from our physics classroom here at Copernic. As you can see behind me, there's a sign that identifies the door to our dark room. That's where we keep our dark matter and dark energy. Bada boom. Where's the rim shot when you need one? Anyway, we're in the process of lining up some additional Friday night live stream programs, and we'll announce those soon. First of all, I want to congratulate all of you students who I believe today was probably your last day of school, and that which it is. So, hope you get a chance to dial it back a little bit, but then we'll talk a little bit about some things you can do later this summer. Now, normally we charge admission for our Friday night programs, but obviously there's not really any way to officially do that here on YouTube. But if you value this program and this kind of program, you can donate by actually clicking on the support the live stream link that's in our channel description, just right below you there. Although if you're in full screen mode, you have to sort of come out of that in order to see that link. But again, it's a free will offering, so if you're in a position to help us out with a donation, we'd greatly appreciate it. This presentation and other live stream videos will be available on Copernic's YouTube channel once this program is concluded. And before we start our program tonight, I just want to bring to your attention that Copernic's summer camp programs, very popular, this year will be online only. We've got 8 different week-long camps that cover a range of topics in science and engineering. The camps will be a combination of live presentation and discussions, along with home activities where the students actually have video access to the Copernic educator running that camp. Our first camp will actually start on June 29th, and it'll be a camp on weather disasters, from floods to tornadoes. So go to Copernic's website for more information on those camps and links to our online registration portal. Now let's transition to tonight's program. Did you know that between June 5th and July 5th of this year, there have been 3, or will be 3 eclipses? It's pretty rare to have so many eclipses so close together in time. So let's get to know more about eclipses. Tonight, Zoe Luna Ponterio, who's above here on the screen, is the manager of SPIF, the Spacecraft Planetary Image Facility at Cornell University. And she'll be presenting a talk entitled In the Shadows, The Wonder, Beauty, and Science of Eclipses. Zoe is no stranger to Copernic, having made a number of presentations at Copernic here on a wide range of astronomical topics over the past few years. We're very glad to be able to have you back here again, and this time we brought her right into your home. So you'll various times during this presentation, you'll be able to ask Zoe by asking questions in the chat box here in YouTube. So Zoe, thanks again for presenting here at Copernic, and this time your commute home should be a lot faster. So Zoe, I'm going to turn the live stream over to you as soon as you unmute yourself.
All right. Thank you for that introduction, Drew. Am I coming through okay? Excellent. All right, I'm going to go ahead and put that in there. So we should now have our slide up, our title slide. So yes, this is a timely talk because we're in what seems to be a bit of a high eclipse frequency. We actually do have one coming up that will be easily viewable, weather permitting, from here on the 4th of July. There will be a partial lunar eclipse visible from here. And so we're going to talk a bit about what they are and what they aren't, what causes them. And what I also want to say about this talk is it's subtly about something more than just eclipses. And I also think that this talk is a bit of a nod to neurodiversity. And if you're not familiar with that term, it's the idea that we have all brains that are different, and some of us have brains that get diagnosed as something that's really unusual. And for myself, I'm talking about ADHD, which I have. And this talk was created in a bit of an ADHD fever pitch of just throwing stuff together, and I honestly had no idea what it was going to be about, except that I wanted to talk about eclipses. And so I just let it run. And in about 2 hours, I had this talk, and honestly, I got shocked by my own plot twist ending. So I get to now take you on this ride, and it's not going to end where I bet you think it's going to end. And I hope that you're surprised and enjoyed a little plot twist at the end. And you can also see like a different way in which a mind works and how that can actually be an advantage. So especially for any kids watching, you feel like, oh, I'm different. It's hard for me in school. Yes, but you can turn it into a strength, and you can come and do cool stuff like work for NASA. Trust me. So with that, let's just jump into it, and we'll start with the basics. So let's see here. There we go. All right. Everyone's probably seen some sort of diagram like this. On the top is what a lunar eclipse is, and the bottom a solar eclipse. So what's going on here? Well, we have shadows, right? And that's where the talk comes from. Eclipses are really about shadows. One thing is casting a shadow on another thing with a light source, in this case, the sun. So even though we call them both eclipses and they both involve the moon and the sun, they're actually very different things. And this is the first thing I want to point out about this picture. So notice that a lunar eclipse is when the moon passes into the Earth's shadow, whereas a solar eclipse is where the Earth passes into the moon's shadow. So moon going into Earth shadow, Earth going to moon shadow. Now, this is different because no matter which of these happens, we are here on the Earth watching it, and perspective is very important. So, from the point of view for a lunar eclipse, everyone on the nighttime side in that picture is seeing it. All right. People that are on the daytime side aren't. And in fact, just I think 1 week ago, there was a partial lunar eclipse. We didn't hear about it because exactly what this picture shows was happening. It happened while we were in daytime, and the other hemisphere ended up getting to see it. But as I said, we get one in a few weeks anyway. Now, a solar eclipse, though, notice that you can only really see it if you're in a very specific place on the Earth. So that is a bit of a difference between the two, in that it's also kind of why it might seem like lunar eclipses are more frequent than solar eclipses, though we will talk about the fact that they actually aren't. So this also we need to point out about the umbra. Drew, can you give me a thumbs up? Can you see my pointer moving around? Oh, no. Okay. That's fine, because I have things to point it out. We need to talk about shadows, because there's two different kinds of shadows. There's the umbra and the penumbra. And if you know French like I do, you recognize that word. Ombre is shadow in French. So this blue dot that I just put up there, that's sitting there, is in what's called the penumbra. And this is your partial shadow area. So if I were to look at the sun with proper solar viewing glasses on, of course, so we're in a spaceship and I looked at the sun, I look in this direction, I can see the sun. So that's a green. Yes, I see the sun. I pan a little bit up, and suddenly I am looking right at the edge of the Earth and can just barely see the sun. And if I keep panning, I can't see the sun anymore. The Earth is in my way. So I see some of the sun, but not all of the sun. So there's some shadow, but not total shadow. Now, if I move myself into this position, now I am in the umbra. This is the total shadow. And no matter which way I try and look to see the sun, the Earth is in my way, and I don't see any of the sun. So you'll see this in our diagrams, where usually the penumbra will be a shade of gray, and then the umbra will be a darker shade of gray or a black. And those are the two different kinds of shadows that we're talking about. So I'm going to start out by diving into solar eclipses. All right, so here's a slightly different view of things. I apologize, I'm not crazy about this diagram. I feel like this is a bit of a flat earther daydream here. The line at the bottom is supposed to be the Earth, and obviously the moon is not nearly that close, but we're just going to go with the math here. It's for geometry. So here we see the umbra and the penumbra are labeled, and we can see that the moon's umbra reaches the Earth, and if you were standing in that umbra at point A, you would see a total solar eclipse. However, at sea, standing in the penumbra, you would only see a partial eclipse. Now, of course, there's a very curious thing about the moon and the sun, and that is that they appear about the same size to us. Now, of course, we know the sun is way, way bigger than the moon, but the moon is also way, way closer than the sun, and it just happens that those two things balance out and they look like they're the same size from Earth. And if that seems like too much of a coincidence to just be a coincidence, I will just remind you that we do live in an infinite universe, and whatever is not forbidden is mandatory. So weird things happen. And this is just one of those weird chances. The moon also has not always been this distance. The moon formed much closer to us. It's moving out at about a centimeter a year. It's just that when humans are around to see these things, we've got this weird little matchup between the sizes. And so the important thing is that that umbra does reach us, but it just barely reaches us. Now, if you're in space and you get to see a total solar eclipse, it's a pretty cool thing. I'll play this really quick here. So you can see here that the shadow of the moon crosses over the Earth. And this was, I can sit here and turn the volume off of that. I don't know if you can hear that, but so this was taken by spacecraft watching the Great American Eclipse that happened in 2017. So this is what it looks like from space. All right. So let's now look at what happens during a total solar eclipse. You get this beautiful effect that the moon just is a little bigger than the disk of the sun, covers up the photosphere, and we can see the corona of the sun, as well as any solar flares or prominences that are coming off of the surface. So we're all pretty aware of that effect. However, some of you, when I put this up, might have said, hold on a second, Zoe, I see A, I see C, where's B? And no, my ADHD brain did not totally skip over B. I didn't show you the whole picture. This is the whole picture. So it turns out that our moon is at this perfect distance where it's almost matched up with the size of the sun, but that means, as I said, that that umbra, which extends down in a cone, at that point just kind of barely gets there, but the moon isn't always the same distance from the Earth. The orbit is a little bit of an oval, like all orbits, and so the moon is sometimes a little closer, sometimes a little farther, and it literally dances on either side of that umbra just reaching us or not quite reaching us. So if the umbra reaches us, we get the total solar eclipse, but if it doesn't, you get that situation on the right-hand side, where you get this thing called an antumbrum. And if you're wondering what in the world happens when you're in the antumbrum, I'd like everyone to do a little bit of a home experiment. I want everyone to just hold up their thumb in front of their face, probably close or cover up one eye, and holding your thumb with your arm bent, so holding your thumb pretty close to your face, I want you to look around the room and find an object that your thumb just kind of barely covers. So I'll give everyone a second, look around, find something that your thumb just barely covers with it held kind of close to your face. All right. We've got it. We got one eye open. We're looking at our thumb. It's covering something just barely. Now I want you to extend your arm and move that thumb away from your face without moving your head. And hopefully what you just saw was that as you move your thumb away, it looks like it gets smaller and stops covering the entire object that you were covering. And that's exactly what happens here. The moon's a little farther away and it doesn't cover all the sun, even when it's perfectly lined up. And you get what's called an annular eclipse. And if you want to know what that looks like, it's pretty awesome. Because here it is. The moon is almost perfectly centered on the sun. Sometimes you might see artistic renditions of the crescent moon where it takes on that shape. And of course, the moon never actually takes on that shape, but maybe whoever started that style saw an annular eclipse and saw this effect. And when the moon finally centers itself, you get this. And that's where the word annular comes from. It means ring. So you get this beautiful color. Now, if you ever get to see an annular eclipse, this is important. You never take off your solar viewing glasses because the sun never gets completely covered. So this one, you don't get to, at this point, take them off and see anything. You leave them on the whole time because there's still the sun. So these things are pretty awesome. Now, when and where can I see one? All right, so here is a map that shows total or annular eclipses and where you can see totality or annularity, I guess the word would be. Um, this one does span back to the August 21st, 2017 Great American one, which you can see swathing across the United States from Oregon down to Georgia. But we are in luck because you'll notice the blue ones are total and the purple ones are annular. So there is going to be an annular eclipse. It says October 14th, 2023, that will come across, looks from Oregon, go down into Texas. So that's going to be another North American eclipse, and it'll be annular. So just as cool and different. And then everyone is buzzing about April 4th, 2024. And that's that blue streak that starts in Texas and goes up to, hello, look, New York. All right, that is going to be a total solar eclipse. And it's going to be, the totality will go over Buffalo, it'll go over Rochester, it'll go over Syracuse. This is going to be in our own backyard. Now, I know April is not the best month around here to count on the weather, but at least if it's cloudy, maybe we won't have to drive very far to get to a spot where there's a break in the clouds. So these maps can be found very easily online. You can see that actually right now, if you look over the other side of the world, 2020, June 21, we are literally just days away from an annular eclipse that is going to be starting over Africa, passing over the Arabian Peninsula, and then up over India and the Himalayas, and then through China and out into the Pacific. So I kind of get sad when I see this because I have a friend who takes, like tour groups to go see eclipses, and he had this whole trip planned and this beautiful poster he did. He's an artist, and of course that's not happening, and so a little sad looking at that, but there are still people there who hopefully will get something nice and exciting to look up at on that day. Now, on the subject of the rarity, a lot of people, including myself at one point, mistakenly think that the reason that lunar eclipses and solar eclipses, that solar eclipses are rare compared to lunar, is because, well, look at the size of the shadow. The Earth casts a big giant shadow for the moon to go through, but the moon only casts a teeny tiny shadow. And so that would explain it. But actually, that's not the case. Let's remember that that tiny shadow from the moon still can hit anywhere on the Earth. So you got an Earth-sized target there. And for the other one, for lunar, I mean, you've got an Earth-sized shadow to pass through. So that's not what's really causing the difference. It's really more about the fact that you have to be in such a specific place in the world to see one. Now, one of the things people get asked, of course, is, well, lunar eclipses look like they should happen every time the moon goes around, and solar eclipses should happen every time the moon comes around. So why don't we see one every month? Why isn't there a lunar eclipse every time there's a full moon? And why isn't there a solar eclipse every time there's a new moon? And the reason is because things don't line perfectly up most of the time. The moon's orbit is tilted with respect to the Earth's orbit. And that means that you can look in the upper left there. During most new moons, the moon's shadow passes past the Earth. It doesn't hit it, it misses it because the orbit is tilted. And then you come around to full moon and it misses the Earth's shadow. So the Earth's shadow is long enough, it just passes under or over it. But every once in a while, the situation on the bottom happens where the nodes, they're called, line up so that the tilts cancel and you get it lined up. Now, of course, you don't get a solar followed by a lunar because it takes 2 weeks for the moon to go halfway around, and by then this lineup is gone. But this can produce what we saw, what Drew was talking about, a seeming cluster of eclipses if they all kind of get timed right about when we're lining up these nodes. And so this means that there actually are multiple eclipses happening every year, usually 1, 2, or even 3 that are happening that are visible somewhere. But let's again look at that map. Most of the Earth is covered in ocean, and then you got the polar caps, and then most of the land area is not densely populated. So the reason that solar eclipses seem rare is because of the fact that it's rare for a path of totality to pass over highly populated areas. Whereas, as we pointed out with lunar eclipses, You just need to be nighttime at when it's happening, and everyone on half the globe can see it happening. So this is one of the places where I do want to pause and ask if anyone has questions on solar eclipses. We will also have questions at the end, but I just want to say, like, anyone needs some more clarification on solar?
All right, let me unmute myself here and let me see if we've got any questions. We have uh, almost 30 people watching, 30 families at home. And at this point, I think you have done a fantastic job. No questions quite yet, but uh, we'll keep tabs of that. And when we get to our next break, I'll pass them along, and we can take them from there.
Awesome. Well, we're still in the calm part of the talk, so we'll keep going. All right, we're not quite into the weeds yet. So let's go into lunar eclipses. So just to remind ourselves, we're going to come back to this again and again. Remind ourselves. All right, so lunar eclipse. All right, I found this fun picture on the internet. Oreos, right? Watching it happen. All right. Let's keep in mind that a lunar eclipse is very different from the normal phases of the moon. And if you're just in love with Oreos, don't worry, we got some for that as well. So this is a fun thing you can do with your kids to talk about the moon phases. Can just do this with Oreos. So notice there's some very different shapes. Between these two, you've got an all white and an all black. That's your full and your new moon. That looks similar. There's some crescents in both of these pictures, right? But then there's a lot of differences, right? The first quarter and the third quarter, right? Those don't show up at all in this eclipse diagram. And the gibbous phases, right? No, that never happens with this picture. What actually saddens me though when I see this picture is I thought it was really cute until I read what the label for it was. And they said, look, phases of the moon. I was like, no, that's those aren't phases. That's eclipse. Okay, no. And then what made me even sadder was I realized that it was, I'm not going to say their name, but it was a major amateur telescope manufacturer that posted it on Twitter with that. And I was like, wow, you make telescopes and you don't even know the difference between phases and eclipses. Okay, moving on. Phases and eclipses. There we go. There's a difference. All right. So one of the things I want to reiterate is that idea of the moon is going to pass into the Earth's shadow. So we're here on Earth. We're not the ones in the shadows, right? That's the title of the talk. We're not the one in the shadow. We're watching the moon go into a shadow. And the important thing to keep in mind is that the moon is pretty bright at night, and that even when the moon is in the penumbra, we're not really going to notice it. So the moon does normally pass through the penumbra during full moon, and we don't even really notice it because as long as it's being illuminated by some sunlight, it's pretty bright. So let's look at classic picture of a lunar eclipse happening. This would be a total lunar eclipse. And some of the things you notice right away are that this dark shadow starts to creep across. It kind of looks similar to a solar eclipse, but there's some differences here. And one of them is that the line that's moving across, right, we're used to, and we're going to come back to the Oreos, yep, we're used to that kind of thing, and that's not quite what this looks like. And the reason for this isn't even a lunar eclipse representation. That's a solar eclipse, and I can tell because the Oreo cookies are just slightly larger than the Oreo filling. That is the situation with a solar eclipse. The moon and the sun are about the same size, but not so with this. And I'll just come back to this. The Earth's shadow is bigger than the moon. And you can see that when you look at that picture in the upper right of the screen, right? It almost looks like that first quarter image. And it's because you can tell that that shadow of that Earth is a circle, but it's a circle that's way bigger than the moon. And then it disappears and disappears, and then something kind of weird happens. The moon turns red, and you might have heard this called a blood moon. What is happening here? So that redness actually was sort of there, but as long as some of the moon is being sunlit, the sun is so bright that you can't see that dark red. Your eye is just not able to pick it up. So it's only when the moon gets close to and enters totality that you can see this dark red color. Now, the moon itself is not dark red. So that's not what we're seeing. And there's no sunlight to illuminate it anyway, at least not direct sunlight. So the important thing to also think here is this is the umbra moving across, right? When we're watching a solar eclipse, we get a partial one. Even if it's just the penumbra, we get a show. But again, you only get a show here if you get the moon to go into the umbra. So that shadow is the umbra of the Earth. So what is causing this reddish color to happen? I got a cool little animation here. Here we see a lunar eclipse as seen if you were on the moon, which means you're getting a solar eclipse. And when the sun totally goes behind, it gets dark, but then the sunlight comes through the Earth's atmosphere. And that is this very rich red color. And we know this because, yeah, we've seen sunsets, right? Sunsets look red. And that's exactly what happens on the moon. And then it comes back and it's light again. I'm going to let this go ahead and repeat one more time just so we can take that all in. So at this point, we are entering the penumbra. Now we're in that, but nothing really notices until that umbra is now coming up on us. People on Earth are seeing that umbra go across. Now we just watched it go across our location. And there comes the sunlight, the sunset sunlight coming through the Earth's atmosphere, lighten up the moon with this red color. That's what we're seeing on Earth. And then it's going to come back again. And umbra starts moving across, and there we go. All right, so here's just a really nice still image from that, where we see this light coming through the Earth's atmosphere. It's red for the same reason sunsets are red. That's where the blood moon comes from. Now, how dark red or not red the moon turns is really dependent on what's in the Earth's atmosphere. So things like recent volcanic eruptions can really affect how red or not red the moon actually gets. So that's an important thing to remember here, that the color actually can be changed by what's going on in the Earth's atmosphere. Please tuck that away in your head and save it, because it is going to come up again.
Hey, Zoe,
All right.
I just
Yeah.
wanted to mention that I'm looking at the Earth and I can see all the light pollution.
Yeah.
So everybody turn your lights off when you're not using them.
All right, so this is where I'm going to stop and ask, are there any questions on lunar eclipses? And this is where you might think this, you're like, okay, so the talk's done. We talked about solar eclipses, talked about lunar eclipses, but no, we're just going to pause before we get even deeper into it.
All right, let's see here. Denise asks, is there any place on Earth that never sees an eclipse of any kind?
Ooh, that's a good question. So the answer is no. But of course, since the Earth is tilted, it means that if you were, say, in the North Pole and it was winter, meaning you were tipped away from the sun and the sun was never up, obviously, if a solar eclipse happened and you were there, you would not see it. But you certainly could see a lunar eclipse in that case if one happened. So there is no spot on the Earth that would never get an eclipse, but it is certainly, there are areas that are more difficult to view them from. And the fact that the poles tilt toward or away from the sun can make things kind of tricky.
All right, very good. Catherine didn't have a question, but she did want to give you props for saying thank you for being fierce about moon phases not looking like stages of eclipses. So we thank you for that. Also, there was another question actually dealing with, I guess, solar eclipses, but I guess it could probably relate as well to lunar eclipses. It seemed like when you showed that map earlier, the eclipse, path of totality for solar eclipses seem to be like all over the place. So how often do eclipses happen in the same area?
So the eclipse map can end up looking rather random. I'll go ahead very quickly here and just pop it back up there. And that's because we're dealing with so many different factors. The moon is orbiting the Earth is orbiting the sun, the orbits are wobbling, the bodies are wobbling, they're tilted, they're lining up, they're not lining up. And so there is a rhythm to it. If you look carefully at this map, you'll notice that there's about 2 a year, and then it'll skip a year, and then there's 2 a year, and it'll skip another year. They kind of go back and forth between whether they're total or annular. So it's sporadic, but if you were to look at it over a long period of time, you would see some patterns to it. And of course, the reason that the paths look all weird, they're not just straight, even lines, is because this is a flat map and the Earth is round,
All
and the
right,
shadow is
you're looking
round.
at the Mercator projection there, yeah.
Exactly. So the flat map is just totally distorting these. Also, keep in mind that as the eclipse is happening, the Earth is also spinning. So yeah, there's no straight lines here at all.
All right. Well, yeah, in this particular projection, exactly.
Right.
Although, as it turns out, I think there's a spot in Indiana that oh, actually, okay, I can see your cursor now. This
Oh,
is
there it is.
yeah, right there, exactly. A spot where they got the 2017 uh, totality as well as the 2024 totality.
I
So
think that actually like smacks right on top of Arkansas, if I'm looking at this correctly. So lucky them.
yeah,
They
yeah,
got it.
it's exactly. So book your hotel now.
Oh, where is that? Oh, it's like northeastern Arkansas is southern Illinois, right in there. So that
Right,
that might be a nice spot. Yeah. Wow, they're lucky.
exactly. Um, Alrighty. All right. So I guess what do we press on?
All right. So yeah, where did my brain decide to go from here? Well, of course, since I work mostly on things pertaining to the solar system, at this point in the talk, I was like, wow, I just spent a lot of time talking about Earth and the moon. What about other places? Do other places have eclipses, and what would those be like? And so that is where we kind of go into here. So one of the things we have to understand again about eclipses is, what did I say? I said that the sizes and distances matter. So the fact that the moon and the sun are just the right size and distance, that they look about the same size in our sky from our perspective. The fact that the Earth casts a roughly Earth-sized shadow for the moon to pass into, all of these things have to be kept in mind. Of course, when we leave the Earth, moons aren't the only things that change, right? The size of the sun in the sky is going to change too. So the first thing we have to do is get ourselves in the off-world mindset. So here is the sun viewed from Earth. Now, of course, any picture can zoom in or zoom out and make the sun look as big or as small as it wants to. So I have a series of photos that kind of use this photo as a standard. So let's go in toward the sun first. And if we went to Venus, that's about how much bigger the sun would look in the sky at Venus. And then if we went to Mercury, that's how much bigger the sun would look in your sky. But on the other hand, you might be thinking, why would we even talk about Venus and Mercury? They don't have moons. And you're absolutely right. They don't. So, yeah, they don't get solar or lunar eclipses. So, now we move in the other direction. Mars, all right, that's how much smaller the sun looks from Mars. Now we take a big leap to the outer solar system. There's the sun from Jupiter. And there it is from Saturn and Uranus and Neptune and Pluto is just a really bright star. So the important thing to keep in mind here is that as the sun gets smaller in your sky, it becomes somewhat easier to eclipse it because there's less to block. Now, Mars does have two moons, so that's what we're going to examine first. So, yes, Mars does get eclipses. So these are pictures of solar eclipses on Mars. The top set is Mars's closer and larger moon Phobos passing in front of the sun. We notice very clearly it's not round. Looks like we took this with the Mars exploration rovers, and at the time when we took it, we joked that it looked like someone had thrown a potato in front of the sun for us. But there it is. Phobos is only about 20 miles long at its longest. And so you might say, wow, for something only 20 miles long, it sure blocked a lot of the sun. Phobos is really close to Mars. So that's how it can pull this off. Our moon goes around every 4 weeks. Phobos goes around 3 times a day. Right, this thing is actually in a death spiral. It is doomed millions of years. It's going to either break apart or crash into Mars. It's just the way it is. So obviously, you don't get 3 solar eclipses a day, but it actually turned out to not be too hard to get these. The one at the bottom is Mars's smaller moon Deimos, which is also farther away, so it looks a lot less impressive, but there it is. It does pass in front of the sun. All right, now we're going to jump out to Jupiter, and a lot of people remember this picture went around the internet of, oh my God, Jupiter has a hole in it. Oh, okay, calm down, calm down. No, it's a shadow, right? We're talking about shadows. And so Jupiter's moons, yes, they will get between Jupiter and the sun. Jupiter's huge, so that's really not hard to do. And Io, its moon you see right here, is very close to Jupiter. And so pretty much every time Io goes around Jupiter, it casts a shadow somewhere on Jupiter. So there's almost like a guarantee solar eclipse. So let's remember though, this is what a solar eclipse looks like on Earth, like if you're in space watching it on Earth. And you can clearly see that there's a shadowy region that's kind of blurry, and then there's a dark center. So that dark center is the umbra of the moon, and then we can see the kind of dark-ish region that's the penumbra. But when we look at Jupiter, we don't really see that. It's a very sharp, crisp shadow. What's going on there is that one, the sun is a lot smaller in the sky, and two, Io is a lot closer to Jupiter. And so what's happening is that Io appears much bigger than the sun in the sky, which means that penumbra is a lot smaller, right? If you picture big Io passing in front of little sun, you know, it's not going to take very long from when Io first starts to cross the sun to when it completely passes in front of it. That happens fast because the sun is small. Another way to think about it is to go back to this diagram and realize that as we get up closer to the moon, the penumbra shrinks and the umbra grows, and that produces a sharper shadow. All right, Saturn, yep. Saturn's big and it has moons. Here's Saturn getting double solar eclipses. We got two different moons casting shadows at the same time. So yeah, we get them. And then I actually had this moment of, have we ever seen one beyond that? And sure enough, Google image search, yep, Uranus having its moon Ariel casting a shadow. So Uranus getting a solar eclipse here as well. I hunted and hunted, does not look like we've yet captured a picture of Neptune getting a solar eclipse. This is likely because one didn't happen while Voyager's, you know, went by over a course of days. We just didn't get that lucky. And it's really far away, and its largest moon that would likely cast a shadow, Triton, has a really weird orbit. So I'd have to dig a little deeper to find out, like, could we ever catch a picture? I just am pretty sure there isn't any out there. All right, this is our last breath before we get into the home stretch, and this is also our last breath before things really go off the rails. So any questions on extraterrestrial eclipses?
All right, let's see here. Let's go to the chat and extraterrestrial. One thing actually was more of a comment that did you notice that you could actually see stars during the totality as viewed from Mars?
So the problem with the Mars is that you never get an actual totality, right? The even Phobos is not big enough to block all of the sun. And so that means that no, you're never going to get that beautiful effect that we get here on Earth where the stars come out. If you've ever experienced a partial solar eclipse, I was at the 2017 one here. Even with getting to 70% totality, which is what we hit about here, it was still hard to notice it had gotten darker. And that's because sunlight is just so incredibly bright that our eyes generally adjust for it if it gradually changes. And I actually didn't notice it had gotten dark until it started to get light again. And also it was happening late afternoon, so I think we're all like, yeah, it gets dark as the afternoon goes on. And it wasn't until it started to get bright again that I noticed. So yeah, you really have to have a complete covering. Now, if you went to Jupiter or Saturn, any of those places that were in that shadow and you were in that shadow, you would totally be seeing stars. So you do have to block all of the sun though before you're going to get those stars to come out.
Right, exactly. One of the things that was sort of interesting, going back to sort of lunar eclipses, is there was one back here at 2015, and I when it finally got to totality, all of a sudden, the Milky Way just popped out of the sky. that's one of the things about, when people come up here to Copernic, and they'll look, if the moon is out, like, oh, hey, it's great, you can see it, and you almost go blind looking through a scope at it. But but people who sort of spend time doing astronomy, the moon is this really obnoxious light in the sky. So
Yes, it's like, oh, the moon.
yeah,
Oh.
exactly. So what's really neat is that once it finally went into totality, just whoosh, the Milky Way just popped right out. You could see, all the stars that we normally see up here, and then as soon as it came out of totality, it just collapsed back down again. So
I think
uh,
my experience with that 2015 one was that we had just recently bought our new house, and it has a big giant yard with a farm field behind it. So we're like, "Woo, this will be nice dark viewing." So we went out to the backyard, and of course it's a big full supermoon. We walked back there, we watched it, and we're like, "Woo!" And then it was totality. I got little kids. I'm like, "Okay, we're not going to watch the same thing in reverse. Let's get to bed." And I suddenly looked around and realized that I had not brought a flashlight out because, of course, when we walked out, we had this full supermoon lighting
right.
everything. And suddenly I looked around and I'm like, "Where's the house? Oh my gosh, I can't see anything."
I,
It was
I guess you'll
so
be sticking around here for a little
dark.
while longer. Yeah, exactly.
So we said, "Okay, no, never go out in the backyard without a flashlight. It doesn't matter how bright the moon is." So, all right. Well, I guess I will go ahead
Yeah, let's press on
and
then.
grab you guys by the hand and say, "Okay, and here's why this talk didn't stop here." Because suddenly I looked back at this picture, and I especially looked at the bottom one of Deimos pathetically trying to eclipse the sun, and it actually reminded me more of this. If you know what this is a Venus transit. So this is seen from Earth, and this is Venus passing between us and the sun, so that we're seeing it go against the disk of the sun. And yeah, we also can do this with Mercury, though it's hard to see. It's in the lower left if you look for it there. There was a Mercury transit, if you heard of it. It was last Veterans Day, right? It was November. And up here I heard it was cloudy, but we just happened to be in DC for the day, and we were at the Air and Space Museum, and it was beautiful, sunny, 70 degrees, and we got to see it with their telescope. So it is a little more difficult to spot Mercury, but there it is. And think about it. That way, Venus could potentially see something, right? Because Venus could see a Mercury transit, right? And then I was like, oh, all sorts of things can transit the sun. This is a great shot. This commercial jetliner photobombing this person's attempt at taking a picture of the Venus transit. So, but then this got me to thinking. I was like, wait a second. Hold on, wait. Okay, so the bottom one there is an annular eclipse, but this is a transit, and this is an annular eclipse. And I just started thinking, like, okay, what's the difference? Right? Is it that it's a moon? What's going on here? And I actually did go and Google, what's the difference between a transit and an eclipse? Turns out I did get an answer. A transit is when you don't block the whole disk, which means, yes, technically, what we're calling an annular eclipse is not actually an eclipse. It's technically a transit. And again, annular just because it makes that beautiful ring, which is why, yeah, I wouldn't call anything going on the slide right here annular. I mean, maybe Phobos pulls it off. I don't know, but Deimos is definitely not pulling off a ring. So technically, those are transits. And of course, the minute the word transit kind of started bouncing around in my head, naturally I left the solar system and started thinking about exoplanets. That's planets going around other stars. And the reason is because transiting is how we mostly find these guys. We find them when the planets pass in front of their stars and block some of the starlight. And so here's a nice little animation you're going to see. So here we see a planet has started to cross in front of its star, and here's the brightness of the star has started to dip. So there we go. Starlight dips and then comes back up. And of course, if you put a larger planet there, you see a stronger dip. So not only can we see there's a planet, we can also get an idea for how big of a planet there is. All right, now this effect, honestly, though, is small. So here is an actual piece of data. Here's an actual measurement of one of these dips. And one thing that you'll definitely notice here is up here at the top, this is 100% normal starlight. And that dip only comes down to a little above 97.5%. All right, this is a tiny, like 1, 2, maybe 3% effect. And this is a really pronounced one. There are ones that are less than 1%. So this is small and it's hard to find. And that means there is inherent bias. All right. So we know the word bias means that we tend more toward one thing than another. So here's where we're biased. The top row, all right, the black dots, this is an optical illusion. Those black dots are the same size, and those are our planet. And then the red and yellow are the host star. So clearly, if a star is smaller, then the planet can block more of the starlight. It's a greater percentage, and so it's easier to see the dip happen. So we're biased towards smaller stars. But don't worry, that's actually not a big problem because it turns out that those are actually the most common stars. If you've ever heard someone say that our sun is an average size star, no, it's not. Our sun is a medium sized star, but sizes of stars are not equally distributed. Most stars are small stars, and very few stars are big stars. So while we are medium sized, the majority of stars out there are smaller than the sun. Now, the bottom row shows if the star is the same size, and we just kind of saw this in animation, a bigger planet can block a greater portion of the starlight, which also makes it easier to find. So we're also biased toward finding large planets. So it's been a struggle to find things the size of Earth. At first, the only things we were finding were big, giant planets. So early days of finding exoplanets was finding things like this, Kepler 13AB, which that's how big it is compared to some of the planets in the solar system. And again, it's easier to find it if it blocks more of the light. Now, another problem with this method, and this really thankfully doesn't introduce bias, it's completely random, but you do have to be lined up, right? You need to be viewing this planetary system in a way that you actually will see the planet pass in front of the star. If you happen to be looking, because these are all oriented randomly in space, right? So if you're looking down on it, on its poles, you'll never see the planets pass in front of the star, and you'll never know if there's a planet there. So just because we look at a star and we don't see any dips doesn't mean there's not a planet. Also, I want to bring up the problem of time. All right, Earth takes 1 year to go around the sun. Mercury at the fastest takes 88 days. You get to the outer solar system and you're measured in decades. We have only been looking for exoplanets for a couple decades. So we're coming up on 3 decades, I guess, but we can't sit there and stare at one star for years, right? We usually stare at a star for maybe a few days, a few weeks, and then if something interesting happens, we might go back to it. But that means that we really cannot find things like Jupiter, let alone it's unlikely we would have found anything like Earth as far as being this far away from our star. So we are biased toward finding planets that are really close to their star and therefore have really fast orbits. So here's Kepler 4b. Look at the time in days. Those are Earth days. 3 days, 6 days, 9 days, 12 days. This thing is going around its star every 3 days. Mercury, 88 days. This thing, 3. So this produces a kind of planet we call a hot Jupiter. And one of the most famous hot Jupiters is 51 Pegasi b. And it's famous because it was discovered in 1995, and it was the first exoplanet we found around a main sequence star. It doesn't get to be called the first because a few years before that, we actually found the first planet around another star, kind of by accident, and around a pulsar, which is practically one of the weirdest places we thought to find a planet. So this one doesn't quite get to be first exoplanet, but a lot of people kind of treat it as if it is because it's the first one around a regular star. But it is 20 times closer to its star than the Earth is, so it goes around its star about every 4 days. It is only 50 light years away. That's not that far. Our next star over is only 4 light years away. So this is in our little stellar neighborhood here. There are planets that are 50 times closer to their stars and literally go around in hours. Hours. I know a planet has a 6-hour year. So these places are extremely weird. They're so hot that metal would evaporate and be in the air. It's weird. All right, so here's an example of some raw data just to make your head kind of scratch. And what you're looking at here is most of those are normal starlight, boom. And then there's dips, right? You see dots go down, and that's where a planet passed. And so we say, oh, this planet passed here, and here, 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 here. What's going on? This planet is all over the place. It's not a regular pattern. And then you think, wait a second, we have 8 planets in the solar system. You can have more than one planet. And it turns out, ladies and gentlemen, this is the TRAPPIST-1 system, which we have identified 7 planets in. Count them, 7 planets. So he had to work through all the math to figure out what was causing all the little dips. And there it is. So here are each of those planets individually. And the on the right you see P, that's their period, and the D is days. So the closest one, TRAPPIST-1b, has a period of about 1.5 days. That's how long its year is. All the way up to TRAPPIST-1h, which if you look at the previous one, we only caught it once. There on the bottom. So we have an estimate for its period, but we don't have a solid number yet. The really fascinating thing about this system, though, is that these aren't giant Jupiter planets. So there's a lot going on in this slide. Let's break it down. First of all, the planets are shown accurate relative size. So yes, these are 7 rocky inner solar system sized planets that are there. However, look at their sun. Their sun is that little red thing. Oops, sorry, not quite, little red thing right here. And then the size of the sun would be shown here in this yellow dashed line around it. Sun, relative size. That's how much smaller their star is compared to the sun. And then these orbits are shown to scale to that. So yeah, this TRAPPIST-1b will be only like another sun's worth away. And that means that these guys are all super close. So look at this line. You'd have to take this thing and shrink it down. So look down in our solar system. That's where it would snuggle in, way inside of Mercury's orbit there. So up here at the top, it shows that we're almost more on the scale of Jupiter and its moons, where Jupiter's only a little smaller than TRAPPIST-1, and then the orbits are just a little further away than Jupiter's moon's orbit. So this is a very, very tiny little planetary system. So sizes, this shows all the sizes of everything I just talked about, all on one page, all to scale. So we see our sun really big down here. Then we see TRAPPIST-1 is a very small red dwarf star. Jupiter's just a little smaller. Jupiter's moons are pretty tiny. Here are the TRAPPIST planets. And then there's the inner solar system planets. So this gives you a sense of scale for the sizes of all these things. But the system gets even cooler because you might think all those planets being so close to that star, man, it must be so hot on all of those, right? But no, because smaller stars are also much cooler. That TRAPPIST-1 star puts out a lot less heat than the sun does. And that means if you want to achieve the same temperature, you have to snuggle up a lot closer to that star. And when you do the math to figure out, okay, adjust for that, where are the same temperatures happening? Boom, TRAPPIST-1 and the inner solar system almost perfectly line up. And so we see here, TRAPPIST-D in the middle is almost at exactly the same temperature point as far as sunlight goes that the Earth is. E is just a little ways out. Even F is kind of hanging out in the area of Mars. C looks a little close, it's hanging out with Venus, but let's keep in mind that both Mars and Venus look like they were Earth-like and habitable in their past. So just being there because they look cold and hot now does not mean that you couldn't have a habitable environment there. So this is an artist's conception often drawn of TRAPPIST, where you see that, yeah, the closest one, maybe two, are kind of steamy, but then you got these nice middle ones that might be watery if there's water there, and then you get to the frost line out here, and it's probably kind of frozen. And the other really weird thing is the planets are so close together that if you were to hang out on one of these planets, you would see the other planets in your sky like we see the moon. Like you'd be able to see features on them. They're all so close together. And telescope, man, you'd be able to easily, with a little telescope, see what's going on the other planets. All right, now this suddenly gets me thinking, wait a second. I told you to remember this, right? We said that when you got these lunar eclipses back here on Earth, that the sunlight, even though it was blocked, came through Earth's atmosphere, turned red because of chemicals in the Earth's atmosphere, and that happens here too. So when a planet passes in front of its host star, yes, there's the black of the planet blocking it, but the blue atmosphere of the planet, the starlight is going through it and coming here to Earth, just like what happens in a lunar eclipse here. And that means you can take that starlight that passed through that atmosphere, you can run it through a spectrograph, you can separate it into a spectrum, look for what light came through and what light didn't, and get chemistry. You can tell what chemicals are in the atmospheres of planets light years away, and that, ladies and gentlemen, can lead to searching for signs of life. So we started with eclipses, and plot twist, we ended with aliens. And that's it. Now we get to open it up to any and all questions.
All right, super. Thank you very much. You're right, that did have an interesting twist there at the end. Let's see here. We did have one question from Roy. How good is that 4th of July eclipse going to be for us, and will we be able to see it? Or I think it's the 5th of July.
It's the night of the 4th goes into wee hours of the 5th.
Right. Okay.
So it is only a partial eclipse. So and so assuming weather is good, and hey, July is has a pretty decent chance.
It could happen.
Yeah, exactly. It could happen. So I'm just trying to find where. There it is. All right, so I'll put this up here. So, hello. All right, so what we're going to see then is we're probably not going to get to the red. I haven't looked up exactly how much coverage we're going to get, but we will likely see the black shadow, the umbra, start to come across, and then it'll pass on, and I don't know that enough of the moon will get. Usually you only get that red color at a total eclipse. So I imagine it's going to look like the beginning 4 or 5, and then the last 3 is probably what we're going to see here. So not quite as spectacular, but it'll still be cool to watch,
Definitely. I think, actually, what I'm going to do at the end of this program is I thought I would do a real quick tour with Stellarium of what's going to be up tonight, and I may actually dial in July 4th that evening, and let's just sort of see what Stellarium tells us we'll see here, at least here in the southern tier. Let's see, Olia said, it's more of a comment, but no, there was a question. It says, we went to North Carolina for the last solar eclipse and everything got, somewhat dark. It was like evening, but the most interesting effect was that everything looked silverish. It looked so surreal, not like anything I've ever seen. Why does that happen? Do you have any sense of that?
I've never actually gotten to see a total. I'm really excited for 2024. I'm excited maybe to drive down and see the annular in 23. I imagine what's happening there is that we saw, again, I can bring up the picture. That's right, not too far from here. There it is. I'm going to bet that what you were seeing was the effect of not just starlight, of course, but also this coronal light. Because it's nice and faint, but it does, this is that's what I've seen pictures it really does look like. It's very white and fuzzy, and I imagine that might be what was giving things a very strange illumination, because that's just not something that would be the primary light source in any other time other than that. So I can certainly imagine that would be something your brain would immediately just kind of be like, what's going on? Another weird thing that I really would love to experience is the temperature drop that I hear about.
Right.
I did experience it in 2017. Again, I didn't notice it, on the inbound, but then when it started to come back, I suddenly was like, "Oh, now I'm burning." It was August, and I had I hadn't noticed it going away, but I noticed it coming back, and had to go get my sunscreen. So,
All right, very cool. Let's see, there was actually Phil asked, is what next new instruments will allow us to observe more about these planets? And seeing how you, again, do, you up there in Cornell do a lot of work in this area, anything you can tell us about some new instruments that we might be using for looking and learning more about, through eclipses?
right. So we of course are. I mean, we're doing a lot on this on many fronts. So in the solar system, we've of course got the Parker Solar Probe, which is circling in closer and closer to the sun, and it's going to actually be able to fly through the area of the corona and really tell us what's going on there, because we're still struggling to understand why it's a million degrees there, even though the surface of the sun is only a few thousand degrees. So the study of the sun's corona really started with eclipses. So we're just kind of continuing that. We continue to watch eclipses for purposes of, this is another thing you're not going to possibly see coming, confirming and measuring general relativity. Because there was actually a solar eclipse that helped Einstein really become famous, in that he predicted with his theory of relativity that if space-time was indeed bent by gravity, then that means that the light passing through space would be bent too. And he predicted that during a solar eclipse, you would be able to see stars right next to the sun that were actually behind the sun, but their light was being bent by the gravity of the sun. And the eclipse came, the stars were there, boom, Einstein was right, the
That
light was bent.
that's the
So
gravitational lensing, right?
exactly. So we're still using that as well. We are using micro lensing, looking for exoplanets. We have TESS now, which is our new planet hunter up in orbit. Kepler, where you saw everything was named Kepler this, Kepler that. That was because of the space telescope Kepler that found like our first 4,000 or so, nearly 4,000 exoplanets. And now TESS can look at more stars for longer periods of time. So now we're really chugging. We think that we're going to be up to 10,000 and not too long. But we do follow up with ground based telescopes too. Usually the space telescopes take tons of data, and then we look for like, where do there seem to be interesting ones, and then if we see something interesting, we will follow up with a ground based telescope to try and get better data. What's the orbital period, how big is the planet, what's the density, and therefore what type of planet it is, and then yes, start to probe the actual atmospheres to see, is there water, is there life, things like that. So
Right.
there's a lot of different fronts on which we're exploring these things.
Interesting. Um, Late last year, we had Gary O'Neill, who works down at NASA and is working on the Lunar Gateway project
Yes.
that's coming up. And one of the things we had also talked about was, wouldn't the moon be a good place for an observatory?
Yes. So this is actually something I've been thinking about for a long time, and so have a lot of other people. I actually mentioned that as one of the many things you could do if we established a permanent colony on the moon. Back in high school, I wrote an essay on why we should go back to the moon, and that was one of the things I brought up.
Mm,
So yeah, the moon has no atmosphere. That's a big plus. And the nice thing is also that, well, yeah, you can get above the atmosphere with a space telescope, but having an orbiting telescope introduces a lot of engineering difficulties and complications. Putting a telescope on solid ground is a lot easier. And so being able to go to the moon and put a telescope there that has the advantage of not going through atmosphere, but also the ease of being on solid ground would be amazing. And I actually recently saw a proposed plan to say, why build the whole structure? Just pull an Arecibo, and we already have all these craters on the moon. Just pick a nice smooth crater and make your telescope
yeah.
in the crater. And there you go. And of course, it would be really nice to do it on the far side of the moon, which is the side that never sees the Earth, because then we'd definitely be blocking out any, a lot of the radio signal and other and light pollutions from the Earth. So you'd be able to see things even better.
Excellent. All right. Well, I think you pretty much covered the questions that I've seen come in here, and so again, I really want to thank you. This has been a great presentation, and I think it's clear that while we're not in a position to have people come up here on a ongoing basis, at least for now, this kind of activity I think is certainly well worth doing, and technologically, this is I think my third live stream here, so I'm catching on, and so we'll make some additional tweaks here and there. But so anyway, I guess I would ask you then is, can I get my give me back the host capability, and then I think I'm going to transition to doing a little bit of a stellarium presentation, and we'll take it from there. Again, before people leave, again, if this was something that you enjoyed and you're in a position to, down below in the description, there's an opportunity to support us with a donation through the live stream. And also, again, for those of you who are just watching, maybe for the first time, we are, besides our YouTube channel, we are very active on Facebook, Instagram, Twitter, and so look for us on all those platforms, and it's just a way to keep connected and keep curious here. Anyway, so we thank you much, and let's see, did you give me back? Yes, you did. Okay, so I think what I'm going to do then is host disabled partial screen. All right. Okay, let me go here. All right. So if we go back to gallery view, and I think Mike made a nice donation, and so we will now move on to, let's see if I can get to my display capture and get to the right display. So give me a second, and if I do this, yeah, here we go. So we are going to go to right now. I will turn off my fast forward. So this evening, if we look here in the south, they're going to back up a little bit. We'll turn off some of the, well, actually I'll leave some of the, these are the constellations. You won't see the actual cartoon drawings in here, but we also bring up the time, and we can sort of see what things are. So like right now, it's just a little bit after 8:30. It's still pretty light out, and but as time goes on, if we go to say, let's go up all the way up to 11 o'clock tonight. By the way, this software is called Stellarium. It's free and runs on both PCs and Macs. And so Jupiter is actually going to come up above the horizon right after 11 o'clock tonight. By midnight, we'll see both Saturn and Jupiter. Let's see, they're probably just around 10 degrees above the horizon. Yep. So if you've got a good southeast horizon, you'll see Saturn and Jupiter right around 10 degrees. If we then proceed into the evening, and then by about 3 o'clock, the Moon and Mars will be available. So that would be if you're an early riser or a late go-to-sleeper, those would be some opportunities there. So one thing also I was going to do then also is go to the 4th of July, and let's just sort of see what's going on there that evening. Actually, go back here. So if we'll center on the moon, and so we'll turn off some of the cartoons, and let's see if we can zoom in here, see what might happen. Do you recall about, you said it's, oh, here we go. I think we're now just starting to see a little bit of I thought I saw some of the darkness. Do you know about what time the eclipse is supposed to happen?
I can look it up here in a second. Really quick, I just saw someone on there. They were peeking at my shirt and they wanted to know what the rest of it was.
Oh, okay.
So I will show. Yes, there is a joke on here. If you know the '80s rock ballad,
Okay,
it is
hold
a
on.
total eclipse of the heart.
Ah, there you go.
I forgot that I had put it on. I was going to point it out, but yeah, it's a crop top T-shirt, so it's not what I ever would have worn down to Kopernik. But I was like, it's Zoom.
There you go. Exactly.
All right,
Exactly.
I have it in my calendar here. It starts at 11:07 p.m. Eastern time is what
All
I
right.
have it down as.
All right, 11:07. And so, yeah, I could sort of see maybe a little bit of darkening in this area here, and then it sort of brightens back up again. So, yeah, it's not going to be
So it's going
particular.
to be a itty bit.
Yeah, it's not going to. Yeah.
It didn't seem like it was going to last too long.
Yep. Yep. So.
All right, so very subtle.
Yeah, very subtle. Very subtle. Um, anyway, so I guess that's where we're at, and so you all have a good evening. It's supposed to be nice and clear out tonight, so go ahead and take a look at what's out there tonight. We will be also trying to keep people up to date with what's going on with Doug Hurley. We are very excited that he and Bob Behnken had a successful launch and docking with the International Space Station, and he could well be up there for up to 4 months. And so we will be keep tracking that. There is one of our summer camps actually is called Welcome Aboard the ISS, the International Space Station, and part of that camp will be where we actually have an opportunity to have our students talk to an astronaut on the International Space Station using the ham radio station we have here. Now we'll most likely end up doing that, virtually, if you will, either through Zoom or through a telephone call, but ultimately using the ham station here at Kopernik, talking to either Chris Cassidy or Bob Behnken. Both of them are still our licensed ham operators. But if Doug Hurley's up there, maybe we can get him to float on by and say a quick hello. So that might be fun. So we'll let you know how that works. So anyway, thank you again, Zoe. Have a great summer, and we'll look forward to your next talk when you come down here. And thank you again all for who dialed in, connected in tonight. We will list a number of other programs for the rest of the summer. This has been a lot of fun, and we'll see you soon.
All right, thank you, Drew. Thank you, everyone.
Take care now. Bye. Bye.
Bye.